Hello class, we're going to pick up where we left off last time talking about balancing redox reactions under aqueous conditions. Last time we talked about under acidic conditions and we just began talking about how to balance reactions under basic conditions. When we were last here, we discussed the reaction of lead hydroxide and chlorate to form lead oxide and chloride. And we discovered that the oxidation state of lead changed from +2 to +4, so that it was an oxidation reaction. And we discovered that the chloride, or chlorine rather, began as +1 and ended as a chloride -1, so overall being reduced. So if we were to write the balanced half reactions for this reaction, we would say that lead is being oxidized by 2 electrons, so it produces a lead 4+ and 2 electrons as a product, given that it's an oxidation reaction, and chlorine plus is gaining 2 electrons to be reduced down to chloride minus. So when we balance our reaction actually doesn't change. It goes from lead hydroxide reacting with chlorate to form lead oxide and chloride. What we have to do next is make sure that our oxygens are balanced, because right now our reaction is not mass balanced. So when we move on to the next page, on step 3, we're going to balance the oxygens by adding water and balance the hydrogens by adding protons. This is the same process as under acidic conditions. Only once we're at that step, we're going to convert protons to water by adding hydroxide to both sides. And that is the part that is unique to basic conditions. So let's do that here. For the lead reaction, we have lead hydroxide reacting to form lead oxide. We have 3 oxygens on the reactant side, and we have 2 oxygens on the product side, so we need to add 1 equivalent of water to add an oxygen. Afterwards, we can take a look at our reactant side where we have 3 hydrogen atoms, and our product side we now have 2 hydrogen atoms given the inclusion of 1 equivalent of water, so we need additional hydrogen atoms. We add hydrogen atoms on the right side of the reaction on the product side in the form of protons. We are now at the point where we have oxygen atoms balanced at 3 and 3 and hydrogen atoms balanced 3 and 3, but we're under basic conditions, so we can't have protons floating around. So then we add hydroxide to both sides. So in this final step, we add hydroxide to our product side and hydroxide to our reactant side. When we do that, any protons that we have are quenched with the hydroxide to neutralize and make water. On to the chlorine reaction. We have an oxygen on the reactant side, and we have no oxygens on our product side. So we need to add 1 equivalent of water to introduce an oxygen. We then now take into account that we have 2 hydrogens introduced on our product side. So on our reactant side, we must add 2 equivalents of protons. We're under basic conditions, so this is the next step where we need to neutralize those protons by adding 2 hydroxides. And we need to keep everything balanced, so we also need to add those 2 hydroxides to our product side. The 2 protons react with the 2 hydroxides to make 2 equivalents of water. Now is just some bookkeeping steps where we need to isolate all of our reactants, put them together on the left side of a single reaction arrow, and we need to isolate our products and put them together on the right side of a reaction arrow. So we're going to do that here. Our reactants on the left side of a reaction arrow include lead hydroxide and hydroxide, chlorate, and 2 equivalents of water. So we have lead hydroxide reacting with hydroxide, chlorate, and 2 equivalents of water. On the right side of our reaction, on our product side, we have lead oxide and 2 equivalents of water, and chloride and 1 additional equivalent of water, making 3, and 2 hydroxides. So we have lead oxide, 3 waters, 1 chloride, 2 hydroxides. Anything that is on the reactant side and the product side in equal amount, we can cancel out. So first, we have 2 waters on the reactant side, which cancel with 2 of the waters on our product side, leaving 1 behind. And we have 1 hydroxide on the reactant side that quenches or that balances out with 1 of the 2 hydroxides on the product side, leaving 1 behind. And what we are left with finally is our completely balanced reaction, where we have lead hydroxide reacting with chlorate to form lead oxide, water, chloride, and hydroxide. And that's the end of that problem. In our next topic, we're going to be discussing actual electrochemistry, where redox reactions produce an electric current. So let's take a look at a situation involving a redox reaction that is separated by a wire and a salt bridge, and this is called a galvanic cell, also called a voltaic cell. It involves the spontaneous electrochemical reaction in which the half reactions are separated so that current can flow through an external wire. So what we're going to do is first focus on the anode side of our reaction. So that's everything shown in magenta. The anode reaction is where the oxidation occurs. So the oxidation is occurring where we have this electrode, which is made of copper, gets oxidized to form copper 2+. When that happens, we have a half reaction that can be described as such, where we have copper solid reacting to form copper 2+ in an aqueous solution, producing 2 electrons. So here we have 2 electrons as a product, and this is a dissolution reaction because we have something that's a solid forming something that's aqueous in solution. So this is a redox reaction that is also a dissolution reaction. On the other side of our galvanic cell, we have a redox reaction where we have silver ions in solution precipitating and getting reduced to form silver, which is our cathode. So in our reduction reaction, we have our cathode. Our cathode is our reduction reaction because we have silver gaining an electron to form silver solid. This is a precipitation reaction. We have something that's in solution forming a solid. It's a precipitation. It is also a reduction because silver plus is gaining an electron. So to recap so far, we have the anode, which is our left side of our reaction typically drawn, where we have an oxidation reaction, where we have the electrode is the anode, it's getting oxidized. On the right side, we have our cathode, where we have our electrode is a cathode, and we are precipitating silver onto that electrode as a reduction is taking place. Now, when this occurs, we have copper reacting to produce electrons. Those electrons are actually traveling through a copper wire and ending up at the cathode where they are acting as a reactant. So we have these 2 electrons go through a copper wire to then reduce silver to form silver plus. This is not yet balanced, but this is showing the transfer of electrons, an electron as a product, electrons as a reactant. Now, there's one more piece of information that's critical to the success of a galvanic cell, and that is the salt bridge shown here. This salt bridge is connecting the 2 beakers, and these are beakers, I should say, of solution. And the salt bridge is composed of sodium nitrate, shown here. We have sodium. Anytime sodium is bound to something, when it's not in its elemental form, it's going to be a +1 ion because it's isoelectronic to neon. Here we have the Lewis structure of nitrate. We see that there are 3 formal charges on it, which equate to being a -1 charge overall. So we have a plus and a minus. This is a nice salt. When copper is oxidized and goes into solution, the solution on our anode side is a 1 molar copper nitrate solution. It must be paired with an ion because you can't just produce cations in solution. So what happens is 2 equivalents of these of nitrate comes out of the salt bridge to react and form a salt with the copper that's being produced. On the cathode side, where we are reducing silver, if we reduce silver and it starts precipitating out, we would have a buildup of nitrate in solution. So what happens there is the sodium that is left unpaired after nitrate goes and reacts with copper 2+. That sodium comes over here and binds with the nitrate that's being left behind as silver gets reduced. So silver gets reduced, it produces a bunch of nitrate in solution, and sodium comes out of the salt bridge to pair with the nitrate to form more sodium nitrate salt. So everything's interconnected and every piece of this must exist. Your solution of copper nitrate at the anode, an electrode that's being oxidized, a salt bridge that's forming a salt, reforming the salt in solution, electrons being transferred over to the cathode where it reduces silver out of the silver nitrate solution onto the electrode. And so over on the anode side, we have a reaction of copper 2+ reacting with nitrate to form copper nitrate. And that's connected to the salt bridge, which is also producing the sodium ion to react with the nitrate that forms from that half reaction to form sodium nitrate. Now that we've seen what the big picture looks like for a galvanic cell, all of this information, or the critical pieces of the information, can be summarized in what's called standard cell notation. So here we have that same scenario, but written more succinctly, where we have different quadrants separated by single and double vertical lines. So let's take a look. So from left to right, it is always written anode and cathode. So left, we have our anode, which is our copper solid. That's separated by a barrier from a reduction barrier, where we have our reduced species and our oxidized species. So we have copper being oxidized to copper 2+, and that's our solution that is in the galvanic cell. This whole thing is separated by a double vertical line indicating a physical barrier, so they're physically separated from one another, where we have at our cathode a silver solution that's aqueous 1 molar being reduced to a silver solid, which is our cathode. Let's take a look now at a standard cell notation for a galvanic cell involving chromium and copper. So here we have chromium, oxidized copper, reduced copper. So the left side is our anode, that's our oxidizing side. On the right side, we have our cathode, which is our reducing side. So we have chromium solid oxidizing to form chromium 3+ and producing 3 electrons. On our reduction side, we have copper 2+ gaining 2 electrons to form copper solid. So how do we balance these reactions? Well, we cross multiply. We take our oxidation reaction and multiply it by 2, and we take our reduction reaction and multiply it by 3. And what we're left with is 2 equivalents of chromium solid react to form 2 equivalents of chromium ion, producing 6 electrons, and we have 3 equivalents of copper 2+ being reduced by a total of 6 electrons to form 3 equivalents of copper solid. So now we have 6 electrons being transferred, and that is a balanced and equal transfer of electrons. Finally, what we're going to do is a little bit of review and classify the following 2 reactions as either redox or acid-base. So in the first reaction, we have sulfuric acid reacting with zinc to form hydrogen gas and zinc sulfate. So there are 2 things that you need to look out for immediately. First is whether or not you have a strong acid. If you have a strong acid, you could very well have an acid-base reaction. But the second thing that you need to look for simultaneously at the same time as the first thing is whether or not you have the elemental form of any type of element. And in this reaction, we have 2 of them. That should lead you to believe that you probably have a redox reaction. So let's take a look. We have zinc solid. That's the only time zinc's going to be a 0 oxidation state. In the product, zinc is paired with sulfate. Sulfate has a 2- charge. That means that zinc is 2+. And there we have it. We now know that this is a redox reaction because zinc is being oxidized. We can also have taken a look at hydrogen gas. That's the only time hydrogen gas is going to be, or hydrogen as an element is going to be in the 0 oxidation state. In our reactants, it's +1 because 2 of them are paired with sulfate, which is -2 overall. So we have protons being reduced to form hydrogen gas, and we have zinc being oxidized. Finally, if we wanted to prove that this is a redox reaction and not an acid-base reaction, we can take a look back at our strong acid. For something to act as an acid, it needs to donate a proton, and another thing needs to accept the proton. But overall, the protons have to stay protons. So here we have 2 protons associated with sulfate. In the product, we don't have any protons anymore. We have hydrogen gas. That is a different form of hydrogen altogether. So we do not have an acid-base reaction. Here we summarize our half reactions for the redox process, where we have zinc 0 being oxidized to zinc 2+ and producing 2 electrons. 2 equivalents of protons react with 2 electrons to form 1 equivalent of hydrogen gas. That's a redox reaction. Next, we're going to take a look at the reaction between calcium oxide, 2 equivalents of nitric acid to form calcium nitrate, and water. So first, again, you got to look for whether or not you have strong acids or strong bases. We have a strong acid. Nitric acid's a strong acid. The next thing to look out for is, do we have anything in its elemental form? No, 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 no. We do not. So we have oxidation states here that are non-zero. So this could very well be an acid-base reaction. So if we have a strong acid like nitric acid, that's going to produce 2 protons. What happens to those hydrogen atoms in the product? Do they stay as protons? Well, they end up on water. That's the only thing in the product side that has hydrogen atoms. And if we take a look at water and we break every bond in it and consider it being completely ionic, once again, as we see very commonly, oxygen gets a 2- charge, which leaves each of these hydrogen atoms with a +1 charge, meaning that they are protons. So we go from 2 protons in the reactant side to 2 protons in the product side. That's an acid-base reaction because that's a transfer of protons. If we wanted to convince ourselves that we did not have a redox reaction, we could go through that whole thing. We would find that oxygens are all staying as -2, and that has a ripple effect. But the one that we would really want to look at is what happens to calcium here. So we have calcium oxide as a reactant. Oxygen is going to be -2, calcium is going to be +2. Nitrate overall is a -1 charge, and we have 2 of them, so calcium would be 2+, so calcium goes from 2+ to 2+. Everything is staying the same. So we have a nitrate in the reactant, nitrate in the product, so nothing in nitrate is going to change oxidation states. So, and we have oxygen with a -2 from calcium oxide to -2 in water. So nothing in this reaction is changing oxidation states. Okay, so now we know that we have a acid-base reaction. Let's write out the elementary steps for proton transfer. So our acid is 2 equivalents of nitric acid producing 2 equivalents of nitrate, which shows up paired with calcium, and 2 equivalents of protons. Those 2 protons are going to react with the oxide from calcium oxide to which acts as a proton acceptor, as a base, to form water in our product. And that's where we're going to end today.